All right, good morning, everyone. We are now recording. So our plan for today is to finish off revisiting inverses and orders of permutations, but now using our newfound cycle form of a permutation. And then we'll see how easy or how quick it is to compute the orders of permutations when they're written in cycle form. We hinted at this last day already that it was going to be the least common multiple of the cycle lengths, but we'll see that in particular today. And then we'll get into the next topic, which is chapter 5, and that is, now that we've got this theory of permutation, at least the building blocks of it underneath us, we can go back and revisit our puzzles, swap puzzle, etc., and see how to use permutations to represent things like positions and move sequences on those puzzles. So now we're going to connect the theory with the practice. And so that's our goal for today. So let's just pick up where we left off last day. We were looking at finding inverses of permutations. Now that we've written our permutations in cycle form, the way we can find the inverse is just to reverse the order in which the numbers are written in the cycle form. So this is, for example, the alpha permutation 14732. We just reverse the numbers 23741, and that's the inverse permutation. Our convention is to put the smallest number in the cycle at the beginning. And so in this case, we could just shift the numbers around in the cycle so that 1 appears first. And that would be reading it from, again, left to right. I find the 1, and I sort of read them as, there's the 1. So then it's, the next number is 2, 3, 7, 4. So 1, 2, 3, 7, 4. I just read them around in the cycle because it doesn't really matter where I start. All that matters is whatever number is being put in, the number to the right of it is what comes out. The alternative way, and the way I typically do this to finding inverses, is I just do what I showed in the last step there. If 1 is the first number in the cycle, by convention, it's already written in with the smallest number first. We might as well keep that as the smallest number first. So I write down the number 1, and then I reverse the remaining numbers, 2, 3, 7, 4. And that's the inverse. So we've got a nice way to find inverses of permutations. And that is summarized there as, to find the inverse of a cycle, you just write the cycle backwards. Okay, so what if it is a product of cycles? What if our permutation is a product of disjoint cycles? Well, there we just use our rules for finding inverses of products, which we already discussed last day, and that was, if I have alpha as a product of permutations, sigma 1 through sigma k, then the inverse would just be sigma k inverse, sigma k minus 1 inverse, and so on down to sigma 2 inverse, sigma 1 inverse. So in other words, the inverse of a product is the product of their inverses in reverse order. This was the idea of, if you put your socks on, then your shoes on, the inverse of that is take your shoes off, then your socks off. You have to do the reverse and also do them in the reverse order. So invert and in the reverse order. However, because disjoint cycles commute, it means that it doesn't matter which order I write sigma 1 to sigma k in. Because they commute, this could be written in this order. And that's always nice to know, because it says that if I want to take the inverse of a product of disjoint cycles, I just do the inverse one at a time. And I can keep them in the same order. It doesn't matter, because disjoint cycles commute with each other. So let's see how we can do this in practice. Let's find the inverse of alpha. So to find alpha inverse, that's the product of those 3 cycles. I can compute the inverse of them individually, but I can keep them in the same order because they are disjoint and they would commute with each other. It wouldn't matter which order I multiplied them in. So I go for the first one. the smallest number, I keep it in the first position, and I reverse the remaining numbers, 9, 4, 5. The next permutation has got the 3 there, and then I write the remaining numbers in reverse order. There's only a 7, so I just keep it as 7, and then a 6, and write the remaining in reverse order, which is 8, 10. So really, the only things I was doing was reversing the orders of these remaining ones, like this. And that's the inverse. So there we go. We've got the ability to compute inverses of permutations, whether they are just a single cycle, or products of disjoint cycles. We can compute them rather quickly now. Okay. Let's have a look at, I think there was another example down here. Oh, maybe I didn't put another example down here. You might as well do another example. Find the inverse of beta equals 374 and 5, 9. So go ahead and take a moment just to find that inverse. And once you found the inverse, you can pop it into the chat. And so now this, you can see that even in terms of popping things in the chat, it's a lot easier to pop these permutations in the chat over the array form. In the array form, we couldn't really write arrays in the chat, so we just write the second row. But now we can write the full permutation in the chat window, just through text, using the round brackets, etc. Yep, looks like we're getting some results in. So beta inverse is 347. And I'm just reading it off the chat, exactly 5, 9. So we got our inverses. The thing to keep in mind is that whatever the cycle structure is for the permutation, the inverse has the same cycle structure. And by cycle structure, I mean alpha was a 4-cycle, a 2-cycle, and a 3-cycle. And its inverse is a 4-cycle, a 2-cycle, and a 3-cycle. Beta is a 3-cycle and a 2-cycle, and its inverse is a 3-cycle and a 2-cycle. And so that's one of the things that's beneficial, is that inverses have the same cycle structure, because as we'll see in a second, the order of a permutation, it only depends on the cycle structure. Okay, so let's go back and revisit the order. The order of a permutation, as a reminder, is the smallest number which kills it, or the smallest power, which when you raise the permutation to that power is the identity. We can use cycle forms to eyeball the order. So how do we do this? Well, one way to sort of think about this is in terms of the picture. We've got this permutation beta. And what it does is it takes 1 to 3, 3 to 2, 2 to 5, and 5 back to 1. So that's our permutation beta. And the smallest number, the smallest power, the smallest number of times I've got to compose beta with itself to get every number to return back to where it started is going to be 4. Because every time I take beta times itself, I just skip once along around that cycle. And so beta to the 4 is going to be what takes 1 all the way back around to 1, 3 to 3, 2 to 2, and 5 to 5. So we have that the order of beta is 4, since beta to the 4th is equal to the identity, but beta 3 is not the identity, beta 2 is not the identity, and beta 1 is not the identity. Okay, so why did I write this out in this long way? I just want to emphasize that what is the order? It's the smallest positive power, the smallest positive integer, which will turn that permutation into the identity. And here, beta, beta squared, and beta cubed, they don't turn out to be the identity, because one application of beta takes 1 to 3. 2 applications of beta takes 1 to 2. 3 applications of beta takes 1 to 5. And it's not till the fourth application that 1 goes back to 1. Okay, so you don't have to write that out every time. I'm just trying to emphasize here that this is the idea behind the order. It's the smallest one that turns it into the identity. And the thing to note here is that the order is equal to the cycle length. Okay, so that's a nice observation to make, is that we can immediately see what the order is just by counting how long the cycle is. And that's the general statement down there. In general, the order of an M cycle is M. So let's determine what the order is of this next permutation. Alpha is consisting of a 2 cycle and a 3 cycle. So alpha looks like 1, 3, which goes like that, and then a 3 cycle, which is 2, 4, 5, back to 2. And so what I notice with this one is that I'm trying to find the smallest power for which I can kill it. So the thing to note is alpha to any power is 1, 3, 2, 4, 5 raised to that power. But these are disjoint cycles, so they commute. And because they commute, it means that we can raise each one of them to the individual power. Okay? So alpha to the power k is just the 2 cycle raised to the power k, and the 3 cycle raised to the power k. Now, I'm going to scroll back and try to find the spot where we actually, there it is. I'll make it to the top. So right up at the top of the page, if alpha beta commute, then raising the product to a power of m is equivalent to just powering up each piece, alpha to the m times beta to the m. And that's all we're using here. Disjoint cycles commute. Doesn't matter which order I multiply them in, so I can do the powers on each one individually. So that's our key step. And then we say, well, if this is to be the identity, right, I want this to be the identity because I want to find the order. So this is the identity when k is, well, I'll say it this way, when 2 divides k. So when 2 divides k. So how do I kill a 2 cycle? I just have to make sure I multiply it to itself an even number of times. Because an odd number of times, 1 will end up at 3. It goes 1 to 3, back to 1, then to 3, back to 1, then to 3. So in order for 1 to come back to itself, I have to do it an even number of times. And this is equal to the identity when is that the identity? When is raising a 3 cycle to the power of k the identity? Yeah, I see some comments already coming in. So this is when, sort of, this is inherent in your answer. This is when 3 divides k. In order to kill a 3 cycle, you have to apply it to itself 3 times, or 6 times, or 9 times, or 12 times. So some multiple of 3. And so that means then alpha to the k is equal to the identity when 2 divides k and 3 divides k. Or in other words, when 6 divides k. What is 6 in this case? This is the LCM of 2 and 3. So the power that kills alpha is the least common multiple of the 2 powers that kill the 2 cycles. So what's the smallest power that kills alpha? We've got that a power k kills alpha when it's divisible by 6. So the smallest one has to be 6 because that's the smallest number divisible by 6. So therefore, the order of alpha is equal to 6. So in short, we need to apply it some number of times so that 1 goes back to itself. So that's an even number of times. But 2 also has to go back to itself. So that's a multiple of 3 times. So it's got to be a multiple of 2 and a multiple of 3. And that's the least common multiple is 6. We need the smallest multiple. So in this case, we can look at this next example. What is the order of beta, which is made up of a 3 cycle, a 3 cycle, and a 4 cycle? So the order of beta is going to be just the smallest power, which kills a 3 cycle, kills a 3 cycle, and kills a 4 cycle. So it's got to be a multiple of 3 and a multiple of 4. And it has to be the least common multiple of 3 and 4. And so that's 12. Maybe I'll say least common multiple of 3, 3, and 4, just so you can see that all I'm doing is writing down the cycle lengths and then computing the least common multiple. Okay, so that's it. That's how we compute orders. Orders of a permutation in disjoint cycle form, you just have to read off the least common multiple of their cycle lengths because you need to kill each one of the cycles. But we can elaborate on this a little bit more. We can say more about this, not just the orders. We can say something like, what is the cycle structure of beta cubed? If I took beta and I cubed it, what is the resulting cycle structure of that? Well, that would be, beta cubed would be this cubed times this cubed times this cubed. Disjoint cycles commute, so when I power it up, I can power their individual cycles up. Yeah, exactly. It'll kill those 3 cycles. Bang, those are dead. Ooh, that's the identity. That's the identity. And what did it do to the 4 cycle? What does it do to the 4 cycle? Yeah, the cycle structure is 4. You got it. The cycle structure is 4. And the question is, how do we know it? Well, this last one, if I take a 4 cycle and raise it to the power of 3, I can do the multiplication. I can go 6 goes to, and then I'm just taking 3 hops. So 1, 2, 3. So 6 goes to 11. 11 goes to 1, 2, 3. 11 goes to 10. And then 10 goes to 1, 2, 3. 10 goes to 9, and then 9 has to come back to 6 because there's really nothing else for it to do. And so we see that this is a 4 cycle. So in other words, I didn't get the 4 cycle shrinking to, say, the product of 2 cycles, for example, by raising it to a power, a 3. It stayed a 4 cycle. In fact, it turned into beta inverse if you look closely enough. Sorry, not beta inverse. It turned into the inverse of the cycle. Sorry, not beta inverse. There we go. It turned into the inverse of this cycle. The cube of that 4 cycle turned out to be the inverse of it, which is not beta inverse because beta inverse still has the 3 cycles involved in it. So this turns out to be a 4 cycle. How about beta to the 4? What kind of cycle structure does that have? If I took beta and I raised it to the 4th power, does anything die off? Does anything survive? It kills the 4 cycle. You got it. So beta to the 4th kills the 4 cycle. And the 3 cycles, they're not killed. So 6, 9, 10, 11 to the 4. That turns out to be the identity. Those 3 cycles are not killed. But the 3 cycles are unchanged. Exactly. They're unchanged because to raise it to the 4th power is the same as multiplying it to themselves 3 times and then multiplying 1 more to it. But multiplying to themselves 3 times is the identity. So these things turn out to just be themselves. And so this is 2 3 cycles. That's the cycle structure. Those turn out to be, these just observations of what happens when I power it up, those turn out to be very powerful observations that we're going to use to solve problems on the Rubik's Cube. We're going to be able to see things like, okay, that cycle structure, it's a 3, and a 4 cycle. Oh, if I raise it to the 4th power, I kill that 4th cycle. And I leave those remaining 3 cycles unchanged. So doing beta to itself 4 times ultimately just does those 2 3 cycles. So those are some powerful observations. We don't yet see how this is actually going to help us on the cube, but and the other puzzles, but we soon will. And we'll get to that within the next couple of lectures. We'll see how that happens. So here's another question. If alpha has order 7, what is alpha to the 35? What about alpha to the 106? So we saw questions like this in the last lecture, but it's always good to revisit these kinds of things. So if alpha has order 7, what is alpha to the 35? What does that equal? So alpha has order 7. So I'm going to raise it to the power 35. Yeah, it's the identity. And that's because that's alpha to the 7 raised to the power of 5, which is the identity to the power of 5, which is the identity. What about alpha to the 106? What is that? First of all, is it the identity? If not, oh, it's itself. Very nice. Yep, it's itself. And that's because it's alpha to the 105 times alpha. And alpha to the 105 is alpha to the 7 times 15. So 7 times 15 is 105. And then there's a extra alpha to the power of 1 that's there. So that multiplying all those things together gives us alpha to the 106. And this is equal to the identity. So that's equal to alpha itself. And the power on what results ended up just being the remainder of 106 when you divide it by 7. And that's this last theorem, which it's the theorem from the previous lecture. Just, oh, sorry, this is the order permutation theorem. Sorry, I was jumping ahead of myself. The order of a permutation written in disjoint cycle form is the least common multiple to cycle length. So that's our main theorem, which tells us how we can compute orders. Here's an example on the Rubik's Cube. So if I do this move sequence, move the right face. So if I move the right face, it'll look like the left face to you, but that's just because my screen is mirrored. So I move the right face and move the up face. And I look at how the pieces moved. Then that produces a permutation on the pieces. So the pieces have moved around. What is the permutation? It turns out that if I put numbers on each of the stickers, and those represent the location, home location, and then where they move to, that it's a permutation of those numbers. We will get into the details of this in later lectures. I'm just sort of assuming that, if we do this, then what we get is a permutation. The permutation we get is this one. It's going to be a 15 cycle. So there's 15 stickers that all get permuted amongst themselves. There's a 3 cycle, and then there's 2 7 cycles. We can actually have the computer work this out for us, which we will. And then we could ask, what is the order? So if I do that move again and again and again, so RU, 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 and I keep going, when do I eventually get back to where I started from? Well, this is going to be the least common multiple of 15, 3, 7, and 7. And that's 105. So it means I'd have to do the move 105 times. And so we can predict things that can happen just by working out the cycle structure of the move sequence. Okay, so this is just a sort of referring to or alluding to or foreshadowing to how we're going to use these kinds of ideas later on. Let's look at the next example. Alpha is a 3 cycle and 2 cycle. If alpha to the k is a 3 cycle, what can you say about k? So if alpha to the 3 is a, sorry, alpha to the k is a 3 cycle, what can we say about k? So any ideas? Yeah, it would have had to have killed the 2 cycle, and in order to kill the 2 cycle, you have to be even. You have to be a multiple of its order. So exactly, what can you say about k? We have that alpha to the k is 243k, 15k. If this is to be a 3 cycle, this means alpha, I'm sorry, not alpha, this means the 2 cycle, 15 to the k would be the identity, which means k is even. We'd have to have killed that 2 cycle because the 2 cycle is going to be for an odd power, it's just going to be the 2 cycle, or for an even power, it's going to be the identity. So it's either going to be there or not. And that depends on whether it's odd or even. So if we don't want that 2 cycle to be present, it's got to be gone, which means k had to have been even. Okay. And so the last result, which was this was the theorem that we had last day that said, if alpha is a permutation and we raise it to a power of m, and m actually kills it, then what can we say about m? M had to have been a multiple of the order. We can't kill a permutation with anything other than the order or a multiple of the order. And I wanted to prove this. So we've used this now. We introduced it last chapter. We've used it now, but it's worth proving just to see how the ideas of divisibility theory that we developed can be used to prove results like this, just to see how all these things sort of fit together in terms of arguments. So I want to show that the order of alpha divides m. So the first thing I do is I would say, well, by the division algorithm, we can write m as a multiple of the order plus a remainder. So we can write it as q k plus r, where I'm going to let the order of alpha, just so I don't have to keep writing ord alpha, I'm just going to call that k. So where k is equal to ord alpha. And this is for some remainder r, which is between 0 and k. So in other words, m is killing alpha, so write it as some multiple of the order plus a remainder. This is not strange to us because we just did it back here for this example. We had 106 and we had the order was 7. So what we did was we wrote 106 as 7 times 15, and then there was a 1 here as an exponent of the alpha. That's our remainder. So 106 was a multiple of 7 plus 1. That's how we used it in practice. This is how we're going to do it in general. So alpha to the m is equal to alpha to the k to the power of q times alpha to the r. So that was that 106 is 7 times 15 times alpha to the 1. This is equal to the identity, since k is equal to the order of alpha. And so this is equal to the identity times alpha r, or alpha to the r. And so what do we have now? Well, we're assuming that alpha to the m is the identity. So I just circled the statement inside the theorem. Alpha to the m is the identity. So that means we have that this whole thing is equal to the identity. What does that mean? It means that we have alpha to the r is equal to the identity, where r is less than k and bigger than or equal to 0. So r is a number that's smaller than k but kills alpha. R is a number that's smaller than the identity, sorry, smaller than the order. So R is a number that's smaller than the order of alpha, but yet it still kills alpha. So how could a number that's smaller than the order actually kill alpha? And the answer is it can't if it's a positive number, because the order is the smallest positive number that will kill it. So if R does kill alpha, it means it had to have been 0. So therefore, this implies that R is equal to 0, since R is smaller than the order of alpha. So it can't actually kill it unless it's 0 itself. And if R is 0, then I look back at this expression here, and I say, well, if R is 0, then that means m is equal to k times q, which means that k had to divide m. In other words, the order of alpha had to divide m. So that's the end of our proof. Okay, so I just wanted to show you how those results from number theory come into play here that we developed, divisibility, remainders, and whatnot. The takeaway from this is now we know that if a power is going to kill a permutation, it has to be a multiple of the order. Only multiples of the order can kill permutations. Any other power will not kill it. In fact, any other power will be equivalent. So alpha to the m, whatever m is, it would be equivalent to alpha to the r, where r is the remainder. And we saw that already. So I haven't really said anything new here other than what we've seen in these examples. So we've got that alpha to the 106 turned out to be just alpha. And that's because the power on alpha in the end is just going to be the remainder of that 106 divided by the 7. And that was 1. So we could just use that theorem now that says alpha to the 106, oh, it's 1 more than a multiple of 7. So alpha to the 106 has to equal alpha or itself. So that's how we can use that result. In other words, it's about thinking our way through and not actually calculating. So we didn't have to raise alpha to itself 106 times to know that its result was going to be alpha. Instead we took, rather the brute force of calculation, we took a more higher level point of view and thought our way through it theoretically. Okay, so that takes us to the end of this section on cycles. You've got all the information now to work through all of the questions on the homework assignment. There was just a couple of things at the end here which you probably needed, and now we've got those. So the next thing I want to do is get to our puzzles again. So now we've got the foundation of permutation sort of laid out, and now we can go ahead and see how we can work with puzzles. So how are we going to do this? Well, there's a couple of things that we need to represent on puzzles. We need to represent a position, the current position of the pieces. And we also need to represent a move. So if I do a move, I want to be able to say this move that I did, it corresponds to this permutation. In other words, I moved the piece from box 2 to box 5. I moved the piece from box 5 to box 1. I moved the piece from box 1 to box, etc. Those are the kinds of things I want to describe with permutations. And if you think about it, I pretty much just did describe them as permutations because I described them as a function. The piece in box 2 went to 5, so 2 goes to 5. 5 went to 1. 1 goes to wherever it goes. So those are the two things we need to describe. How to take a position of the puzzle and represent it as a permutation, and how to take a move sequence that has been done to the puzzle and represent it as a permutation. And so we'll do those two things. So we're always going to assume for this puzzle position going to a permutation, we're always going to assume that the pieces are in their home locations originally. And then the position that they are currently in now, the scrambled position, is what we get by figuring out how the pieces actually moved. So how do we do that? Well, the description here, definition 5.1.1, tells us how to get from the position that we're looking at to the permutation. And the way we do that is we're constructing our permutation alpha, which represents the position, as follows. If the piece that's labeled I is now in the position that's labeled J, then we say I has gone to J. So the piece in position I has gone to position J, or the piece that, I say it here as the piece that was labeled I has gone to position labeled J, but you can also think of it as the piece that whose home position is I is now in the new position J. So let's think about how to get this in this example. So I've got the pieces all mixed up here on a swap puzzle with 5 objects. So I'm going to look and say, okay, where did the piece 1 get moved to? It moved to box 5. And then how about piece 2? How about piece 3? How about piece 4? And how about piece 5? So those are all the things I want to. These are all ditto marks, meaning that the statement above carries down. So where did the piece 2 get moved to? So piece 2, its home location is normally box 2. Where did piece 2 get moved to? It got moved to box 4. Piece 3, it now is in box 5. Piece 4, it now resides in box 2. And piece 5 now resides in box 1. So that means the permutation corresponding to the position, which we'll call alpha here, is 1 went to 5, 5 went to 1. And, sorry, let me see, piece in box, piece, oh, I wrote 5 and I should have wrote, I messed up on the first one. I was going to say, that doesn't add up, as there is no swap happen here. Piece 1 has moved to box 3. I should have actually picked that up because 5 was twice in the right-hand side. Okay, so now that I've thoroughly confused you, okay, let's restart. Piece 1 is now in box 3. Piece 2 is now in box 4. Piece 3 is now in box 5. Piece 4 is now in box 2. And piece 5 is now in box 1. So alpha has piece 1 has gone to 3. 3 has gone to 5. 5 has gone to 1. And that closes that cycle. Then 2 has gone to 4, and 4 has gone to 2. So this was obtained by doing a 3 cycle on boxes 1, 3, and 5, and doing a swap on boxes 2 and 4. We can go to the next one. And this next one, we'll just go right for the permutation. I'm not going to bother writing down that list of things on the side, probably because I made a mistake there, so maybe it's easier just to focus on the permutation itself. But I wanted to give you an indication of the thought process that is behind this. So for alpha, in this case, we want to figure out how to describe this position. So where did piece 1 get moved to? Piece 1 moved to 4. Where did piece 4 get moved to? It moved to box 2. Where did piece 2 get moved to? Piece 2 moved to box 6. Piece 6 moved to box 3. Piece 3 has moved to box 5. Piece 5 has moved to box 7. And piece 7 has moved to box 1. With this cycle notation, sometimes it's hard to know if you missed a number or not. So I just usually count them out in my head. I go, okay, I need 7 numbers. I got 1, 2, 3, 4, 5, 6, 7. Yeah, they're all there. So this is a 7 cycle. Now we don't have to restrict ourselves just to the swap puzzle. We can do the 15 puzzle as well. So again, we'll write out what the alpha is for this one, or the position. And again, we just think about these green numbers. They're the tiles, or they're the pieces that are moved around, and where are they located now? So 1 has gone to 11. Actually, why don't you take a minute or so to do this one yourself. I'll start you off. Piece 1 has moved to box 11. Piece 11 has moved to 13, and then continue on. Probably noticing that this is a fairly long one. So I'll start working through it as well. So I'm at 13. So tile 13 has gone to box 4. 4 has gone to 6. 6 has gone to 1. So I close that one off. Sometimes if you find you may find yourself that you missed that 6 has gone to 1, and you may have written a 1 after the 6 and then just kept going. And that can happen. And then at some point you realize, hey, wait a minute, I'm getting the same numbers. Oh, that's because I forgot to close it off. I forgot to wrap it around. So yeah, you gotta make sure you stop. Once you get back to the number you started that cycle with, make sure you stop. So it happens to me all the time as well. Like I just forget which number. It usually happens with the next ones, right? Like at this next one, I'm going to say, which number haven't I used yet? Okay, I haven't used 2. That's the smallest number I haven't used. So now I start the cycle with that one. 2 has gone to 16. Where did 16 go? 16 is the blank space or the empty tile. And so I just look for the blank. Where's the blank on the board? That's in box 14. So that's now in box 14. So 16 has gone to 14. 14 has gone to 12. 12 has gone to 5. 5 has gone to 7. 7 has gone to 9. 9 has gone to 2. And 2 I started this cycle off with, so that closes it. The next smallest number that I haven't used yet is 3. 3 has gone to 8. 8 has gone to 10, and 10 has gone to 3. That closes it off. Now I have to think, do I have them all? First, quick count of all the numbers. So I've got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 numbers there. So there's one number that's missing. It's got to be a number that's back in its original spot. And so just quickly scan. Oh, 15 is back in its original spot. So 15 goes to 15. That would be our one cycle. So we've got it. There's the permutation that represents the position of the pieces. We can do the other way as well. We can say, here's a permutation that's supposed to represent a position. Draw where the tiles are. So this has told me that tile 1 has gone to box 5. 1 has gone to 5. 2, maybe I'll keep reading it. 1 has gone to box 5. Tile 5 has gone to box 3. Tile 3 has gone to box 2. Tile 2 has gone to box 1. And then the next one. Tile 4 has gone to box 8. Tile 8 has gone to box 4. And so that means 6 and 7 have not been moved. So we can go either way, starting with the position, find the permutation, or starting with the permutation, find the position. So with that position to permutation, it was thinking tile number, what box is it now in? And that's the goes to. Tile I goes to J. Now if I want to represent a puzzle move sequence, so a puzzle move now as a permutation, then I have to think about how did the pieces move from what box to what box. So this is where we describe the permutation as the piece in the position labeled I, or box I, has moved to the position labeled J. So here's an example. I've got the puzzle pieces in the positions 5, 3, 1, 4, 2. And then after I do alpha, they are now in the positions 5, 3, 2, 4, 1. Or they're now in the arrangement 5, 3, 2, 4, 1. To describe alpha, this is what I want to describe now, is what was the move that was done? What was the move that was done? In other words, which boxes had the pieces being moved in? So I'm only interested now in from what box to what box did a piece move. So the piece that was originally in box 1 has now moved to where? So think carefully about this. The piece that was in box 1, which box is it now in? Yeah, it stayed in 1, exactly. That piece is number 5, the piece numbered 5, and it stayed there. So the piece that was in box 1 is still in box 1. It moved to box 1. How about the piece in box 2? It's still in box 2. How about the piece in box 3? Where did the piece in box 3 go to? Yeah, it went to box 5. And where did the piece in box 4 go to? And how about the piece in box 5? So the piece in box 4 stayed in box 4. The piece in box 5 moved to box 3. So that means our permutation is 1 went to 1, 2 went to 2, 3 went to 5, and 5 went to 3. Okay, you do the next one. Try the next one out. What do we have? We have, so it looks like box 1 to box 3. So the piece in box 1 went to box 3. Yep, that's right. The piece in box 2 went to box 6. So that's the tile number 1. Yep, from box 2 to box 6. 3 to 4. 4 to 1. So the piece in box 4 went to box 1. Yep. 5 to 5 stayed. And 6 went to 2. Good. So we've got 1 to 3. 3 to 4. Back to 1. And then we have 2 went to 6. Back to itself. Perfect. Try the next one now. As you try the next one, I'm just going to go grab a drink of water. All right, so how do we do for the next one? So this tells us that piece in box 1 has gone to box 4. I'm just checking to see the post that was made by Jason to make sure I'm agreeing with you. The piece in box 4 went to box 5. Sorry, I'm losing my voice right now. And so 5 went to 1. And then these remaining ones are back in their place.
So yeah, I agree with you, Jason. Looks good. Okay. So that's how we take a position to a permutation and a move sequence to a permutation. And next day, we're going to see how multiplication comes into play. We're going to see that if we start with a position as a permutation and then do a move sequence, we can get the position of the result by taking the product of the position permutation with the move permutation, and that gives us the new position permutation. And then that's how we can model our puzzles. We can model positions and we can model moves, and they work together through permutation multiplication. So I'll stop the record button now.